Hello friends, in our previous discussions we introduced the second law of thermodynamics and applied it to cycles and cyclic devices. In our further discussions we shall apply the second law to processes. We earlier learned that the first law of thermodynamics deals with the property energy and the conservation of it. The second law leads to the definition of a new property called entropy. Entropy is somewhat an abstract property and it is difficult to give a physical description of it without considering the microscopic state of the system. Entropy is best understood and appreciated by studying its uses in commonly encountered engineering processes, and this is what we intend to do. The objectives in this and the later lectures would be to apply the second law of thermodynamics to processes, define a new property called entropy to quantify the second law effects, establish the increase of entropy principle, calculate the entropy changes that take place during processes for pure substances, incompressible substances and ideal gas. Clausius inequality. The second law of thermodynamics often leads to expressions that involve inequalities. An irreversible, that is actual heat engine, for example, is less efficient than a reversible one operating between the same two thermal energy reservoirs. Likewise, an irreversible refrigerator or a heat pump has a lower coefficient of performance than a reversible one operating between the same temperature limits. Another important inequality that has major consequences in thermodynamics is the Clausius inequality. It was first stated by German physicist R.J.E. Clausius, one of the founders of thermodynamics, and is expressed as cyclic integral of delta Q upon T, which is less than and equal to 0. This inequality is valid for all cycles, reversible or irreversible. Any heat transfer to or from a system can be considered to consist of differential amounts of heat transfer. Then the cyclic integral of delta Q upon T can be viewed as the sum of all these differential amounts of heat transfer divided by the temperature at the boundary. The validity of the Clausius inequality. To demonstrate the validity of the Clausius inequality, consider a system connected to the thermal energy reservoir at a constant thermodynamic, that is absolute temperature of Tr through a reversible cyclic device. The cyclic device receives heat delta Q R from the reservoir and supplies heat delta Q to the system whose temperature at that part of the boundary is T, that is a variable, while producing work delta W reversible. The system produces work delta W system as the result of this heat transfer. Applying the energy balance to the combined system identified by dashed lines yields delta WC is equal to delta QR minus DEC. Here delta WC is the total work of the combined system and DEC is the change in the total energy of the combined system. Considering that the cyclic device is a reversible one, we have delta QR divided by TR is equal to delta Q upon T. Here the sign of delta Q is defined with respect to the system, positive if to the system and negative if from the system, and the sign of delta QR is determined with respect to the reversible cyclic device. Eliminating delta QR from the two relations above yields delta WC is equal to TR into delta Q upon T minus DEC. We now let the system undergo a cycle while the cyclic device undergoes an integral number of cycles. Then the preceding relation becomes WC is equal to TR into cyclic integral of delta Q upon T, since the cyclic integral of energy is 0. Here WC is the cyclic integral of delta WC and it represents the net work for the combined cycle. It appears that the combined system is exchanging heat with a single thermal energy reservoir while involving, that is, producing or consuming work WC during a cycle. On the basis of the Kelvin-Planck statement of the second law, which states that no system can produce a net amount of work while operating in a cycle and exchanging heat with a single thermal energy reservoir, we reason that WC cannot be a work output and thus it cannot be a positive quantity. Considering that TR is the thermodynamic temperature and thus a positive quantity, we must have cyclic integral of delta Q upon T less than or equal to 0. And this is the Clausius inequality. This inequality is valid for all thermodynamic cycles, reversible or irreversible, including the refrigeration cycles. If no irreversibilities occur within the system as well as the reversible cyclic device, then the cycle undergone by the combined system is internally reversible. As such, it can be reversed. In the reversed cycle case, all the quantities have the same magnitude but the opposite sign. Therefore, the work WC, which could not be a positive quantity in the regular case, cannot be a negative quantity in the reversed case. Then it follows that WC internally reversible is equal to 0, since it cannot be a positive or negative quantity, and therefore cyclic integral of delta Q upon T internally reversible is equal to 0 for internally reversible cycles. Thus, we conclude that the equality in the Clausius inequality holds for totally or just internally reversible cycles and the inequality for the irreversible ones. Entropy. To develop a relation for the definition of entropy, we need to examine the Clausius inequality equation derived in previous section more closely. Here we have a quantity whose cyclic integral is 0. Let us think for a moment what kind of quantities can have this characteristic. We know that the cyclic integral of work is not 0 and neither is the cyclic integral of heat 0. Now consider the volume occupied by a gas in a piston cylinder device undergoing a cycle. When the piston returns to its initial position at the end of a cycle, the volume of the gas also returns to its initial value. Thus, the net change in volume during a cycle is 0. This is also expressed as cyclic integral of dV is equal to 0. That is, the cyclic integral of volume or any other property is 0. Conversely, a quantity whose cyclic integral is 0 depends on the state only and not the process path, and thus it is a property. Therefore, the quantity delta Q upon T internally reversible must represent a property in the differential form. Clausius realized in 1865 that he had discovered a new thermodynamic property, and he chose to name this property entropy. It is designated S and is defined as delta Q upon T internally reversible. Entropy is an extensive property of a system and sometimes is referred to as total entropy. Entropy per unit mass, designated S, is an intensive property. The term entropy is generally used to refer to both total entropy and entropy per unit mass, since the context usually clarifies which one is meant. The entropy change of a system during a process can be determined by integrating entropy equation between the initial and the final states. Delta S is equal to S2 minus S1 and is equal to integral delta Q upon T internally reversible from 1 to 2. Notice that we have actually defined the change in entropy instead of entropy itself, just as we defined the change in energy instead of the energy itself when we developed the first law relation. Absolute values of entropy are determined on the basis of the third law of thermodynamics, which is discussed in later lectures. Engineers are usually concerned with the change in entropy. Therefore, the entropy of a substance can be assigned a zero value at some arbitrarily selected reference state, and the entropy values at other states can be determined from this equation by choosing state 1 to be the reference state and state 2 to be the state at which entropy is to be determined. To perform the integration of change of entropy equation, one needs to know the relation between Q and T during a process. This relation is often not available, and the integral in equation can be performed for a few cases only. For the majority of cases, we have to rely on tabulated data for entropy. Note that entropy is a property, and like all other properties, it has fixed values at fixed states. Therefore, the entropy change delta S between two specified states is the same no matter what path, reversible or irreversible, is followed during a process. Also note that the integral of delta Q upon T gives us the value of entropy change only if the integration is carried out along an internally reversible path between the two states. The integral of delta Q upon T along an irreversible path is not a property, and in general different values will be obtained when the integration is carried out along different irreversible paths. Therefore, even for irreversible processes, the entropy change should be determined by carrying out this integration along some convenient imaginary internally reversible path between the specified states. The increase of entropy principle. Entropy is an extensive property, and thus the total entropy of a system is equal to the sum of the entropies of the parts of the system. An isolated system may consist of any number of subsystems. A system and its surroundings, for example, constitute an isolated system since both can be enclosed by a sufficiently large arbitrary boundary across which there is no heat, work, or mass transfer. Therefore, a system and its surroundings can be viewed as the two subsystems of an isolated system, and the entropy change of this isolated system during a process is the sum of the entropy changes of the system and its surroundings, which is equal to the entropy generation since an isolated system involves no entropy transfer. That is, S generation is equal to delta S total and is equal to delta S system plus delta S surroundings, which is greater than and equal to 0. where the equality holds for reversible processes and the inequality for irreversible ones. Note that delta S surroundings refers to the change in the entropy of surroundings as a result of the occurrence of the processes under consideration. Since no actual process is truly reversible, we can conclude that some entropy is generated during a process, and therefore the entropy of the universe, which can be considered to be an isolated system, is continuously increasing. The more irreversible a process, the larger the entropy generated during that process. No entropy is generated during reversible processes, that is, S generation is equal to 0. The increase of entropy principle does not imply that the entropy of a system cannot decrease. The entropy change of a system can be negative during a process, but entropy generation cannot. The increase of entropy principle can be summarized as follows. This relation serves as a criteria in determining whether a process is reversible, irreversible, or impossible. Things in nature have a tendency to change until they attain a state of equilibrium. The increase of entropy principle dictates that the entropy of an isolated system increases until the entropy of the system reaches a maximum value. At that point, the system is said to have reached an equilibrium state, since the increase of entropy principle prohibits the system from undergoing any change of state that results in a decrease in entropy. Remarks about entropy. Processes can occur in a certain direction only, not in any direction. A process must proceed in the direction that complies with the increase of entropy principle. A process that violates this principle is impossible. The principle often forces chemical reactions to come to a halt before reaching completion. Entropy is a non-conserved property, and there is no such thing as the conservation of entropy principle. Entropy is conserved during the idealized reversible processes only and increases during all actual processes. The performance of engineering systems is degraded by the presence of irreversibilities, and entropy generation is a measure of the magnitudes of the irreversibilities present during that process. The greater the extent of irreversibilities, the greater the entropy generation. Therefore, entropy generation can be used as a quantitative measure of irreversibilities associated with the process. It is also used to establish criteria for the performance of engineering devices. So friends, here we come to the end of our discussion, and therefore we sum up. The second law of thermodynamics leads to the definition of a new property called entropy, which is a quantitative measure of microscopic disorder for a system. The inequality part of the Clausius inequality, combined with the definition of entropy, yields an inequality known as the increase of entropy principle. Entropy change is caused by heat transfer, mass flow, and irreversibilities. Heat transfer to a system increases the entropy, and heat transfer from a system decreases it. The effect of irreversibilities is always to increase the entropy. So that is it for today. In the next lecture, we shall be discussing more about entropy. Thank you very much.